Welcome back. Let's learn how to find distance between points, lines, and planes. Alright, so this video is all about distance. In particular, we're going to look at how to find 4 different types of distances within the 3D coordinate system. First, we're going to look at how to find the distance between a point and a plane. Then we're going to look at how to find the distance between 2 parallel planes. Then we'll look at how to find the distance between 2 skew lines. And finally, we'll look at how to find the distance between a point and a line. Alright, and before we get started, if you're not familiar with the equations of planes and lines in 3D space, I would recommend that you go back and watch my lesson videos on planes and lines in 3D space, as understanding those concepts is going to be pretty important for this video. Alright, but with that, let's not waste any more time and look at how to find our first type of distance. Alright, so first up, we're going to look at how to find the distance between a point and a plane in 3D space. And we're going to start off by finding a formula for calculating that distance. So we're going to be looking at things in a general sense to start, but then we will look at an actual example later on. Alright, and so if you take a look at this diagram I have here, we have a plane P represented by this plane equation, ax plus by plus cz equals d. That value of d is just a constant value, and then a, b, and c are the components of a normal vector to that plane. And of course, a normal vector is a vector perpendicular to the plane. Alright, so we have a normal vector for this plane P, and we have a point within that plane, point P1, represented by the coordinates x1, y1, and z1. Alright, and so this is our plane, and then over here we have the point that we want to find the distance between. Right, we're going to want to find the distance between this plane and this point P2 with coordinates x2, y2, z2. Alright, and so how are we going to find the distance between a point and a plane in 3D space? Well, the first thing that we have to do is actually identify what the distance is, right? What measurement are we trying to find here? And the distance that we want to find here is going to be the measurement from the point to the plane that is perpendicular to the plane. Right, so not this diagonal distance from this point to this point. That's not going to be the distance between this plane and that point, because that distance would differ depending on what point you use in the plane. Instead, what we want is the distance from the point to the plane that is perpendicular to the plane. All right, and so that is the distance d that we want to find in this scenario. And in order to find that distance, what we will have to do is create a vector between any point in the plane and the point that we want to find the distance between. Alright, and so if we use point 1 that we're given here, that point is in the plane. If we use that point and point P2 to create a vector, it will look like this. That will be vector P1, P2. And then what we can do with that vector is project it onto the normal vector for the plane, and the length or the magnitude of that projection vector will be the distance between the point and the plane. All right, and so let me show you what I mean. Remember that to find a projection vector, you draw a line from the terminal point of this vector to the vector that you're projecting onto that is perpendicular to that vector, and wherever that line reaches to, that will be the terminal point of that projection vector. So in this case, the projection vector will look like this. That vector will be the projection of vector P1, P2 onto the normal vector of this plane. And as you might be able to see from this diagram, this projection vector will have a length that is the same as the measurement of the distance between the point P2 and the plane. All right, so what we find here is that the distance between a point and a plane is equal to the magnitude of a projection vector, in particular the projection of vector P1, P2, a vector created using a point in the plane and the point we want to calculate the distance to, and we're projecting that vector onto the normal vector of the plane. All right, so we want the magnitude of that projection vector. And if you remember when we first learned about projection vectors, that we have a special notation for the magnitude of a projection vector. We call it component projection. So we would say that this distance is equal to the component projection of vector P1, P2 onto the normal vector. This notation represents the same thing as this notation. They both represent the magnitude of the projection vector. It's just 2 different ways to write it. But then remember, we have a formula that allows us to calculate the component projection. It looks like this. the component projection of a vector v onto a vector u is equal to the dot product of those two vectors divided by the magnitude of the vector being projected onto. So in this case, the distance will be equal to the dot product of these two vectors in the component projection. So we'll have vector p1, p2 dot the normal vector, vector n, and that will be divided by the magnitude of the vector that we are projecting onto, which in this case is the normal vector. So we'll have the magnitude of the normal vector. All right, and then just to ensure that we get a positive value for the distance, because we're not interested in negative distances here, we're just looking for the absolute value of this measurement, I'm going to add absolute value bars around that dot product, because a dot product can sometimes give you a negative result, and we just want the absolute value of that since we're calculating distance in this case. But now, we're not going to stop here. We can actually simplify this formula further. What we want to do is actually take the dot product of these two vectors, vector p1, p2, and the normal vector from the plane. And in order to do that, we need to know what the components of those two vectors are, because the dot product is equal to the sum of the product of corresponding components for those two vectors. And so let's quickly figure out what the components of these two vectors are. The normal vector is pretty easy. Remember that a normal vector for a plane will have the components of a, b, and c from the equation of that plane. So if I write that up here, we know that the normal vector will have components of a, b, and c. But then what about vector p1, p2? What will be the components of that vector? Well, we can find them using the 2 points that make up the initial and terminal points of that vector, that being points p1 and p2. So if we want to find the components of that vector, we just have to subtract the coordinates of the initial point from the coordinates of the terminal point. So we'll have x2 minus x1, y2 minus y1, and z2 minus z1. So that will look like this. The x component will be x2 minus x1, the y component will be y2 minus y1, and then the z component will be z2 minus z1. All right, those will be the components of vector p1, p2. And so now that we know the components of these two vectors, we can perform the dot product between them. So we'll multiply the x components together, add that to multiplying the y components together, and add that to multiplying the z components together. And so that will give us that the distance is equal to the absolute value of a times x2 minus x1 plus b times y2 minus y1 plus c times z2 minus z1. All right, and then that's all divided by the magnitude of the normal vector. And we could write out what that is if we wanted to. It would be equal to the square root of the sum of that vector's components squared. So we would have the square root of a squared plus b squared plus c squared. But I'm going to wait to write that out for now. We'll do that when we finalize this formula. For now, I'm just going to leave it as the magnitude of the normal vector, because there's a little bit more simplifying that we can do in the numerator here. What I want to do next is distribute a through this quantity, b through this quantity, and c through this quantity. So if we do that, we'll have that the distance is equal to the absolute value of a times x2 minus a times x1 plus b times y2 minus b times y1 plus c times z2 minus c times z1. All right, and that's still divided by the magnitude of the normal vector. All right, and now in order to simplify this further, what I'm going to do is reorder these terms. I'm going to group them in such a way that we have all of the coordinates involving a subscript of 2 in the front, and then all the terms with the coordinate having a subscript of 1 at the end. And so here's what I mean by that. This will be equal to the absolute value of a times x2 plus b times y2 plus c times z2, and then we will have minus a times x1 minus b times y1 minus c times z1. All right, and that's still divided by the magnitude of the normal vector once again. All right, so I just reordered these terms such that we have the terms with x2, y2, and z2 first, and then we have the terms with x1, y1, and z1 last. All right, and so now notice that these three terms all are negative. So if we pull out that negative sign from those three terms, we could rewrite it like this. We'll have minus these three terms where they are all positive. And now this is where we can make our final simplification. What do you notice about these three terms, right? What is a times x1 plus b times y1 plus c times z1? Do you recognize those three terms? Well, what they are the three constant values that would be on the right side of the plane equation that would be equal to this constant of d, right? If you remember the standard form for the equation of a plane, it looks like this. You have a times x minus x1 plus b times y minus y1 plus c times z minus z1, where x1, y1, and z1 are the coordinates of a point in that plane. And so if you distribute a through this quantity, b through this quantity, and c through this quantity, you will have the terms of a times x1, b times y1, and c times z1. Now they'll all be negative, but then if you move them to the other side of the equation, that's how you get the positive version of those terms, and so you'd have these three terms right here, which are all constant values that we combine together into one constant value d. So these three terms right here are just equal to that constant value d from the plane equation for the plane that we are working with in this scenario. The plane that we are trying to find this distance for, the distance between that plane and this point. All right, and so we can make one final simplification to this distance formula. We will have that the distance is equal to the absolute value of a times x2 plus b times y2 plus c times z2 minus d. And that will be divided by the magnitude of the normal vector, which now I'm going to write out what that would be. That will be the square root of the sum of the components of that vector squared. So I'll have a squared plus b squared plus c squared. And this right here is the distance formula for finding the distance between a point and a plane in 3D space. All right, and so to summarize, if you want to find the distance between a point and a plane in 3D space, given a point with coordinates x sub 0, y sub 0, and z sub 0, and a plane represented by this equation, ax plus by plus cz equals d, then the distance between that point and that plane will be equal to this formula. The absolute value of a times x sub 0 plus b times y sub 0 plus c times z sub 0 minus d divided by the square root of a squared plus b squared plus c squared. Okay, and so now that you know where this formula comes from and why it works, let's take a look at an example where we use this formula to find the distance between a point and a plane. All right, so here's our example problem. We want to find the distance between the point and the plane, and our point is this coordinate point of 0, 0, 0, or the origin, and then our plane is represented by this equation, 2x plus 3y plus z equals 12. All right, and so if we want to find the distance between this point and this plane, we need to use this distance formula, and in order to set this up, we need to know what the values of a, b, c, and d are from our plane. We know that x sub 0, y sub 0, and z sub 0 are the coordinates of our point, but we still need to identify a, b, c, and d. Remember, a, b, and c are the components of the normal vector for this plane, which are the coefficients of x, y, and z from the plane equation. So in this case, those coefficients are 2, 3, and 1. So a is equal to 2, b is equal to 3, and c is equal to 1. And then, of course, the value of d is that constant value that those three terms are equal to. So d, in this case, is 12. All right, and so now let's set up the distance formula. Let's find the distance between this point and this plane. We will have the absolute value of a times the x coordinate. And notice that the x, y, and z coordinates are all 0, so that makes things pretty simple here. We're going to have a times 0 plus b times 0 plus c times 0, and then minus d. So we're going to have 2 times 0 plus 3 times 0 plus 1 times 0 minus 12. So let's write that in here. We'll have 2 times 0 plus 3 times 0 plus 1 times 0 minus 12. All right, but now all three of those terms are going to be 0, because anything times 0 is 0, so we have 0 plus 0 plus 0 minus 12, which will give us a negative 12. We'll simplify that then, but first let's fill in the denominator here. We need to take the square root of a squared plus b squared plus c squared. So we'll have the square root of 2 squared plus 3 squared plus 1 squared. And now if we simplify, like I said earlier, in the numerator, we'll have the absolute value of negative 12, and then that will be divided by the square root of 2 squared plus 3 squared plus 1 squared, which will be 4 plus 9 plus 1, which is 14. And so we have the square root of 14, and then the absolute value of negative 12 will be positive 12, so this is equal to 12 divided by the square root of 14. And that doesn't really simplify any further, but if you do like to rationalize your answers, if you don't like to have a square root in the denominator, you could multiply this answer by a form of 1 of the square root of 14 divided by itself. If you did that, your rationalized answer would be 6 square roots of 14 divided by 7. All right, either of those answers would be acceptable. I personally don't bother with rationalizing unless it really makes my answer simpler. And so I'm just going to stick with 12 divided by the square root of 14 in this case. But if you want the approximate value, the distance is approximately equal to 3.207 and some more decimals. All right, that's if you plug either of these answers into your calculator and get the approximate value. But this is the distance between this point and this plane. Okay, and so that's how you find the distance between a point and a plane in 3D space. And so now let's take a look at our next type of distance. All right, so next up, we're going to look at how to find the distance between parallel planes. And before we talk about how we find that distance, I just want to clarify why we only look at parallel planes when determining distance. And that's because if your planes aren't parallel, then they would intersect. And so the distance between those two planes is not going to be the same everywhere. And let me show you what I mean. If your planes are not parallel, then they will intersect. And so the distance between those two planes is going to depend where you're looking at those two planes, right? The distance between the two planes right here is different than the distance between them right here. And so there is no constant distance between those two planes. If you wanted to find any of those distances that I described, you would be finding the distance between a point and a plane, right? You would be looking at a particular point in one plane and finding the distance between that point and the other plane. It's not really the distance between two planes, because the distance between those two planes is not constant and therefore is going to be different depending on where you are looking at those two planes. All right, and so that's why we are interested in parallel planes when we're talking about distance between planes, because when planes are parallel, the distance between them will be the same no matter where you are looking at those two planes. Now, keeping that in mind, here we have two parallel planes, plane 1 and plane 2. They are both represented by their respective plane equations. However, do notice that they have different values of d. We have d1 and d2. Parallel planes will share the same values of a, b, and c, or the components of a normal vector for those planes. Since they are parallel, their normal vectors will also be parallel, and so therefore the two planes would share those values of a, b, and c. All right, so those will be the same in both equations, but the constant value of d will be different in each equation. So that's why we have d1 and d2. Okay, and so given these two planes, we want to find the distance between them, and that distance would be the measurement between those two planes that is perpendicular to each of them, right? This measurement of distance is a straight line that is perpendicular to each plane. That is the distance that we are interested in here. And the way we calculate this distance is very similar. In fact, it's basically the same to how we calculate the distance between a point and a plane, right? Because here's what we're going to do. To find the distance between parallel planes, we are going to find the distance between one of the planes and then a point within the other plane. Because if you think about it, if I draw a bunch of different points within this plane up here, the distance between this plane, plane 1, and any of the points within plane 2 is going to be the same, no matter which point you pick. Because all of those points are in a plane that are parallel to plane 1, the distance between the plane and those points will all be the same. And so to calculate the distance between two parallel planes, all we have to do is calculate the distance between one of the planes and a point within the other plane. All right, and so the setup would be very similar to how we calculate the distance between a point and a plane. We would look at a point within plane 1, we'll call it point P1, and then a point within plane 2, we'll call that point P2. And then we would create a vector between those 2 points and project it onto the normal vector from plane 1. And so that normal vector might look something like this. That would be the normal vector for plane 1, which would also be the same normal vector for plane 2. But then we would project this vector onto that normal vector, and that projection vector would have the length or the magnitude that is equal to the distance between the 2 planes. All right, and so we can reuse our formula from earlier for the distance between a point and a plane. here is that formula. Remember that x sub 0, y sub 0, and z sub 0 represent the coordinates of the point that we are calculating the distance to from the plane. So that would be point P2. So if point P2 has coordinates of x2, y2, and z2, we would say that the distance is equal to a times x2 plus b times y2 plus c times z2 minus d, which in this case, that value of d would come from plane 1, right? The plane that we are using to measure the distance to that point P2. So that value of d would be d1. So I'll write in minus d1, and then we have the absolute value of that divided by the square root of a squared plus b squared plus c squared. All right, and so this is how we would calculate the distance between these two planes, but we can actually make a very nice simplification to this formula. If you look at these three terms right here, a times x2 plus b times y2 plus c times z2, what would those three terms together represent? Well, it's very similar to how we got this value of d1 when we found the formula for the distance between a point and a plane. These three values are all constant values, and added together would be the constant value of d2 from the plane equation for that other plane, plane 2, right? The plane that contains that point P2 whose coordinates we are using in this formula. If we were to look at the standard form of the equation of the plane for plane 2 using this point P2, that would look like this. We would have a times x minus x2 plus b times y minus y2 plus c times z minus z2. And so you would multiply a through this quantity, b through this quantity, and c through this quantity. And so you'd have the three terms of a times x2, b times y2, and c times z2, which would all be constant values that we move over to the other side of the equation and group together to be that constant of d2. And so what we can do here is rewrite these three terms as that value of d2. All right, and so what we'll have here is that the distance between two parallel planes is equal to the absolute value of d2 minus d1, and that's divided by the square root of a squared plus b squared plus c squared, the magnitude of the normal vector for both of those parallel planes. And so this right here is the distance formula for finding the distance between two parallel planes. And so to summarize, if you want to find the distance between parallel planes, given the equations of two parallel planes, where you have ax plus by plus cz equal to d1 and ax plus by plus cz equal to d2, then the distance is equal to the absolute value of d2 minus d1 divided by the square root of a squared plus b squared plus c squared. Again, remember that parallel planes share a normal vector, and so those values of a, b, and c in both equations will be the same, but what won't be the same are those constant values of d. So that's why we have d1 and d2. We take the difference of those values, take the absolute value of that, and divide by the magnitude of the normal vector. All right, and so let's take a look at an example where we use this distance formula. And so here's our example problem. We want to find the distance between the parallel planes, and we have our two plane equations right here. We have 3x minus y plus 2z equals 6, and 6x minus 2y plus 4z equals -4. And then down here, I have the distance formula that we just found for us to reference. Now, before we go ahead and use this formula, do notice that with our two plane equations here, that the values of a, b, and c do not match up. That's a problem. You want those values of a, b, and c to match up before you can use the d values in this formula. Okay, that's a very important thing to remember when using this formula to find the distance between two parallel planes. Even though these two planes are parallel, you don't want to use those two values of d until your values of a, b, and c match up. And so how do we fix this issue that we have here? Well, what you want to pay attention to is if one of your plane equations is not fully simplified, or in other words, if it can be reduced by some factor. And if you look at our second equation here, notice that each of these terms are divisible by 2. 6 and -2, 4 and -4 are all divisible by 2. And so if we divide that equation by 2, that will give us the following equation of 3x minus y plus 2z equals -2. And now notice that the values of a, b, and c, or the coefficients of x, y, and z in these two plane equations now match up. They are the same. we have 3 in front of x, -1 in front of y, and +2 in front of z. All right, and so now that those coefficients match up, where the values of a, b, and c are the same, we can use these two constant values of d in this formula. All right, and so you can see that using -2 versus -4 is going to make a difference in this answer. If we didn't reduce this equation into this equation, we would be using the wrong value of d. All right, so that's something that you want to keep in mind with these examples. Don't use this formula unless those coefficients of x, y, and z match up for those two plane equations. But now we can see that d1 will be equal to 6 and d2 will be equal to -2. Those are the values of d from each plane equation. And don't get caught up on which of these two values are d1 and d2. Even if you swap them, if you said that d1 was -2 and d2 was +6, that's not going to affect your answer for the distance, because in this formula, we're taking the absolute value of the difference between those two values of d. So even if you swap the order, the absolute value bars will ensure that you get the same answer either way. All right, so do not worry about which of these two values is d1 and d2. It's not going to matter because of the absolute value bars. And so let's set up our formula here. We're going to have that the distance is equal to the absolute value of d2 minus d1. So we'll have -2 minus 6. So I'll write -2 minus 6. And then we are dividing by the square root of a squared plus b squared plus c squared. And so let's identify what a, b, and c are. They're going to be the coefficients of x, y, and z from our two plane equations. We can see that a is equal to 3, b is equal to -1, and c is equal to 2. So we will have the square root of 3 squared plus -1 squared plus 2 squared. And now if we simplify, we'll have the absolute value of -8, because -2 minus 6 is -8, and that will be divided by the square root of 3 squared plus -1 squared plus 2 squared, which is 9 plus 1 plus 4, and that is equal to 14. So we have the square root of 14 in the denominator, and then the absolute value of -8 is +8, so the distance is equal to 8 divided by the square root of 14. And that will be the final answer to this example. And once again, just like with our other example, if you don't like having square roots in the denominator, if you like to rationalize your answers, another correct answer would be 4 square roots of 14 divided by 7. You would get that if you multiplied this answer by a form of 1 of the square root of 14 divided by itself. All right, if you did that and then simplified, this would be the rationalized answer that you would get. In either case, the approximate value of the distance here will be 2.138 and some more decimals. Okay, so that will be the distance between these two parallel planes. Okay, and so that's it for this example. That is how you find the distance between two parallel planes. And so now let's look at how to find our next type of distance. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so next up we're going to look at how to find the distance between two skew lines. And remember, skew lines in 3D space are two lines that are not parallel, but also do not intersect. All right, and so here I have two skew lines drawn, lines L1 and L2, and what we want to do is find the distance between these two lines. And that seems like a difficult task at first, but what's going to be helpful in determining the distance between two skew lines is realizing that any two skew lines in 3D space will be contained by parallel planes. We could create two parallel planes where each of them would contain one of these two skew lines. And so let me show you what I mean. I've now added two planes to this diagram, in particular two parallel planes, planes that do not intersect, and you can see that one of those planes contains line 1 and the other plane contains line 2. And so in order to find the distance between skew lines, what we can do is find the distance between the parallel planes that contain them, right? Since these planes contain the lines, the distance between those planes will also be the distance between those skew lines. And so that's the distance d that we want to calculate. And we already looked at how to find the distance between two parallel planes. That's the previous type of distance that we just got done looking at. And so we don't really have to invent a new formula here. However, we do have to discuss how we find two parallel planes from the equations of two skew lines. Right, because in an actual example, we're not going to be given the plane equations for the parallel planes containing the skew lines. We're just going to be given the equations for two skew lines. And so in order to find the distance between those skew lines, we have to have a method for finding the parallel planes that they are contained in so that we can then find the distance between those planes. And so that's what we're going to go over here real quick. There's a 4-step process that we can follow to find the parallel planes that contain skew lines. The first step will be to find the direction vectors for each of the skew lines, and we'll call those vector v1 and vector v2. Vector v1 being the direction vector for line 1, and vector v2 being the direction vector for line 2. And we'll talk about why we need those direction vectors in just a second. But the second step is to find a point on each of those lines. All right, and we'll call those points P1 and P2. Now, both of these two things, the direction vectors for the lines and the points on these lines, are going to be pretty simple to find because both of those things are built into either the symmetric equation or the parametric equations for lines in 3D space. All right, so we will be able to identify the direction vectors and the points pretty easily. And then once we have those vectors and points, we can then move on to the next step, which is to find the common normal vector for the parallel planes. And that normal vector will be equal to the cross product of the direction vectors from the lines. All right, and now let me explain why we need this normal vector. If we want to find the distance between these skew lines, we need to find the distance between the parallel planes that contain them, and so we need to find the equations of those parallel planes. And remember that in order to find the equation of a plane, you need two things. You need a point in that plane, and you need a normal vector. Right? We're going to need a normal vector for each of these planes. However, they are parallel planes, so they will share the same normal vector. And so we really only need to find one normal vector, which is what we call the common normal vector. Now, the reason we can find that common normal vector by taking the cross product of vector v1 and vector v2, the direction vectors from these lines, is because those direction vectors will be parallel to their respective lines. And so therefore will also be parallel to the planes. And so we would have two vectors parallel to those planes, and taking the cross product of any two vectors will give you a vector that is perpendicular to both of those vectors. So if we find a vector that's perpendicular to vectors parallel to these planes, then that vector will also be perpendicular to the planes. That will be the normal vector that we want to find. Okay, and so then once we have that common normal vector, we can use that normal vector along with a point from each line that would be in each plane to create the equation of each of those parallel planes, which is step 4. We want to use the normal vector and point P1 and then the normal vector and point P2 to make two plane equations and then calculate the distance between those two planes. Okay, so using the normal vector and point P1, we can create the equation of the plane containing line L1, and then using the normal vector and point P2, we can create the equation of the plane containing line 2. And so then we'll have two plane equations that we can then use to calculate the distance between those parallel planes, which will also be the distance between the skew lines. All right, so that's the process here. There's no new formula. We're just going to reuse that formula for the distance between two parallel planes. But before we can use it, we do have some other steps to take care of, which is where finding the distance between skew lines is a little bit different than some of the other distances that we have found so far. Now, with that being said, we're not going to look at an example of finding the distance between skew lines in this video, as they're very time-consuming problems. However, there will be one in my examples video for this topic, so be sure to check that out if you want to see these steps in action. Okay, but with that, there is still one more type of distance that we need to take a look at before we close out this lesson. All right, so finally, we want to find the distance between a point and a line in 3D space. And so here you can see I have a line L and a point P. We want to know the distance between this point and this line. Now, the distance that we are talking about here is the measurement from this point to this line, where that measurement is perpendicular to the line. All right, so that would be this distance right here. The measurement between the point and the line that is perpendicular to that line. That is the distance d that we want to find. And so how do we go about finding that distance? Well, what we have to do is make use of a point on this line. And so let's say we're working with a point right here along this line. And what we want to do is create a vector using that point and the point that we've been given. And so that vector might look something like this. I'll call this vector vector u. And then between this vector u that we drew and the line, there would be an angle, right? There would be an angle here that we could represent with theta, okay? And then you might also notice, now that we've drawn this vector u, that between that vector, this line, and the distance that we want to find, that we have formed a right triangle, right? We have a triangle here with a right angle. And so what we can do to find this unknown distance is make use of a trig function that will relate this angle and some sides that we do know to find an unknown side, right? I'm referring to SOHCAHTOA. This helps us remember how to relate an angle of a right triangle to the sides of that triangle. Sine of the angle is equal to the opposite side divided by the hypotenuse. Cosine of the angle is equal to the adjacent side divided by the hypotenuse. And tangent of the angle is equal to the opposite side divided by the adjacent side. And so if we're looking at this angle right here, this angle of theta, what two sides do we want to relate in order to find that distance? Well, for one thing, we want the opposite side, because this side, or this measurement of distance, would be the opposite side from that angle. And so we're not going to be working with cosine, because cosine doesn't involve the opposite side of the triangle. We're either going to work with sine or tangent. And so then which of these do we actually want to use then? Well, it's going to depend on whether we know what the hypotenuse is or whether we know what the adjacent side is. And so looking at our triangle here, the hypotenuse would be this side right here, the longest side of the triangle. And the length of that side would be the magnitude of vector u, right? This whole side is vector u, so the length of it would be the magnitude of vector u. So we would know what that is, unlike this side, which would be the adjacent side, which is represented by part of our line. We don't really know what that measurement is. We don't know what the length of that is. So we don't want to work with the adjacent side, which means that tangent is a no-go, and we are going to work with sine, which will allow us to relate this angle to these two sides, the side that we want to find and a side that we already know, the magnitude of vector u. Okay, so here's what we can set up here. We now know that sine of the angle theta will be equal to the opposite side divided by the hypotenuse. The opposite side is the distance, and the hypotenuse is the magnitude of vector u. So we have the distance divided by the magnitude of vector u. Okay, and now if we want to know what the distance is, we should solve for d, and we can do that by multiplying both sides by the magnitude of vector u, and doing that will give us that the distance is equal to the magnitude of vector u times sine of theta. And so that's nice and all. We now have an equation that will allow us to find the distance between a point and a line in 3D. However, it's going to be very unlikely that we know what this angle of theta is, right? We would probably have to figure out what that angle is. We would need to use our formula for finding the angle between two vectors, in particular vector u and the direction vector for this line. But that seems like a lot of extra work that we don't want to do. So what we can do is actually get rid of this angle from this equation or this formula by manipulating this equation a little bit. And what we're going to do here is multiply both sides of this equation by the magnitude of the direction vector for this line. All right, remember that a direction vector for a line is the vector that would be parallel to that line. So that direction vector would look something like this. We'll call that vector v. It could lay over top of the line. Doesn't really matter. The point is that it's a vector parallel to our line. And so what we're going to do is multiply both sides of this equation by the magnitude of that vector. And when we do that, something interesting is going to happen. we'll have that the distance multiplied by the magnitude of that direction vector will be equal to the magnitude of the direction vector times the magnitude of vector u times sine theta. And now we have something that we can rewrite. Do you recognize this expression right here? The magnitude of a vector times the magnitude of another vector times sine of the angle between those two vectors, right? These two vectors are here, and so theta would be the angle between them. And so we have the magnitude of those two vectors multiplied by sine of theta, which if you remember back to the cross product, this is another way to represent the magnitude of a cross product, right? So we would have that the distance multiplied by the magnitude of vector v is equal to the magnitude of the cross product between vector v and vector u. When you multiply the magnitude of two vectors together by sine of the angle between them, that is another way of finding the magnitude of those two vectors cross product. And so now we can solve for the distance here by dividing both sides by the magnitude of vector v, and that will give us our final formula, and I'm going to write it up here, that the distance is equal to the magnitude of the cross product between vector v and vector u divided by the magnitude of vector v. That is the distance formula that we will use to find the distance between a point and a line in 3D space. Okay, and so to summarize, if you want to find the distance between a point and a line, this is the formula that you want to use. The distance is equal to the magnitude of the cross product between vector v and vector u divided by the magnitude of vector v, where vector v is the direction vector for the line that you've been given, and where vector u is the vector created using the point that you've been given and a point on the line that you've been given. All right, you subtract the coordinates from the point on the line from the coordinates of the point that you've been given. The point on the line is the initial point, and the point that you've been given is the terminal point. Okay, so use those 2 points to create vector u. You take the cross product of vector u with vector v and divide by the magnitude of vector v. Okay, so now that you know the formula for finding the distance between a point and a line and how it works and what you need to use it, let's take a look at an example. All right, so here's our example. We want to find the distance between the point and the line, and our point has coordinates of 3, -1, 4, and our line is given to us with a set of parametric equations. We have x equals 3t minus 2, y equals -2t, and z equals 4t plus 1. And then down here I have that formula that we just found, which will allow us to find that distance. And so we want to set up this formula, but in order to do that, we need to know what vector v and vector u are. Now vector v is the direction vector from our line, and then vector u will be created using this point that we've been given along with a point from our line. So what we need to do here is identify a direction vector from this line and a point on this line. And we can do that pretty easily if you remember how a set of parametric equations for a line are constructed, or in other words, if you remember the general form of a set of parametric equations for a line in 3D space. It looks like this. You have x equals a times t plus x1, y equals b times t plus y1, and z equals c times t plus z1. The values of a, b, and c are the components of the direction vector for that line. In other words, the coefficients, or the values in front of the parameter t, make up the components of the direction vector, and then x1, y1, and z1 are the coordinates of a point on that line. All right, and so for this line, if we want to find the direction vector, the components of that vector will be the coefficients of the parameter t, so that will be 3, -2, and 4. So our direction vector will have components of 3, -2, and 4. And then for a point on this line, we want to look at those extra values being added or subtracted from the term with the parameter t. So that would be -2 and then 0 because nothing is being added or subtracted to -2t, and then we have 1. All right, so a point on that line will have coordinates of -2, 0, and 1. All right, and so now we have a point on this line and a direction vector parallel to this line. And so now all we have to do before we can calculate the distance between this point and this line is find that vector u. All right, that vector u will be created using the point on this line and the point that we've been given. The point that we found on the line will be the initial point, and the point that we've been given will be the terminal point. Okay, so what we're going to end up doing here to find the components of vector u is subtracting the coordinates of this point from this point, the coordinates of the initial point from the terminal point. And so vector u will be equal to the vector with an x component of 3 minus negative 2, which will be the same as 3 plus 2, which is 5. So we have 5, and then the y component will be negative 1 minus 0, which is negative 1, and then the z component will be 4 minus 1, which is 3. Okay, and so now we have both vector v and vector u, which means that we can now work on finding the distance between this line and this point. And our next step will be to take the cross product of vector v and vector u so that we can take the magnitude of that vector and divide it by the magnitude of vector v. All right, so let's calculate the cross product here. We're going to find the cross product of vector v and vector u. So let's set up a 3 by 3 matrix to calculate the determinant of. We'll have our standard unit vectors in the first row, and then the components of vector v in the second row, and the components of vector u in the third row. So we'll have 3, negative 2, 4, and 5, negative 1, 3. And now if we calculate the cross product here, we'll start by looking at vector I, cross out the row and the column that it's in, use these 4 values to calculate a 2 by 2 determinant. Negative 2 times 3 is negative 6, minus 4 times negative 1, which is negative 4. So we have negative 6 minus negative 4 times I, and then we will subtract our j term and add our k term. All right, now for j, we'll cross out the row and the column that j is in and use these 4 values to calculate a 2 by 2 determinant. 3 times 3 is 9, and then we'll subtract 4 times 5, which is 20. So we have 9 minus 20. And then let's look at k. We'll cross out the row and the column that k is in and use these 4 values to calculate a 2 by 2 determinant. We'll have 3 times the negative 1, which is negative 3, minus a negative 2 times 5, which is a negative 10. So we have negative 3 minus negative 10. And now let's simplify. Negative 6 minus negative 4 is the same as negative 6 plus 4, which is negative 2. So this will be equal to negative 2y, and then we have minus 9 minus 20j. 9 minus 20 is negative 11, but if we're subtracting negative 11j, that will become plus 11j. And then we have plus negative 3 minus negative 10. Negative 3 minus negative 10 is the same as negative 3 plus 10, which is 7. And so we have plus 7k, so I'll write plus 7k. All right, and so that is the cross product of vector v and vector u. Now what we want to do is take the magnitude of that vector and divide it by the magnitude of vector v. So let's do that. The distance between the point and the line will be equal to the square root of the sum of these components squared, the components of the cross product vector. So we'll have negative 2 squared plus 11 squared plus 7 squared. Negative 2 squared is 4, 11 squared is 121, and 7 squared is 49. So we have 4 plus 121 plus 49, and we're dividing by the square root of the sum of the components squared for vector v, right? That will be the magnitude of vector v. So we have 3 squared, which is 9, plus a negative 2 squared, which is 4, plus 4 squared, which is 16. So we have 9 plus 4 plus 16. And if we simplify, this will be equal to the square root of 174 divided by the square root of 29. And if we simplify that, I'm going to write it like this. We'll have the square root of 174 divided by 29. And then 174 is actually divisible by 29. It's equal to 6. And so our final answer here is that the distance is equal to the square root of 6. That is the distance between this point and this line. Okay? And if you want the approximate value, the square root of 6 is approximately equal to 2.45 and some more decimals. Okay? And so that's it for this example. But before we close off this lesson, one thing that I want to make a note of here, I don't believe I mentioned this in any of the examples in this video, but when you are working with vectors in these problems where you're trying to calculate a distance, it's very important that you do not reduce or multiply your vectors by any scalar value. All right, when you're calculating distance, it's very important that you work with vectors as you find them or as they've been given to you. All right, so when you find a direction vector from a line like we did in this example, don't multiply this vector by a scalar multiple of 2 or divide all the components by 1/2. Don't do that because distance is built into these numbers. And so if you were to change those numbers in any way, that will affect the distance that you're calculating. Okay, so do be careful about that. Whenever you're calculating distance involving planes and lines, be sure to leave your vectors as they are. Don't try to use scalar multiples of them. Okay, and so with that, that is it for this video. And so if you want to see some more examples for all the different types of distance that we looked at in this video, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.